Our next question is, why must everything be so binary? And in this question, we want to talk about how to make predictions for binary outcomes. And I want to be very specific about what I mean by a binary outcome. Here, instead of there being two continuous values where we're trying to find the linear relationship between one and the other, there's one continuous value, and there's one value that's a binary value, a 0 or 1. Here, literally, it's a true or a false. Is x's greater or less than its mean? And so if we look at the values of x's, there are some, real valued numbers. And here, if we look at the values of y's, it's either a true or a false. Well, I could use a linear regression here. And so if I use a linear regression to try and predict what the y's are given the x's, it will give me a slope and an intercept. And if I use that slope and the intercept to try and figure out, what predictions I'll give you, see, oh yeah, I predict 0, I predict 1, 1 being true and 0 being false. But if I look at the scope of the predictions, I start to see some weird things. Like the minimum predicted value is negative 0.9. The maximum predicted value is 1.8. The only top possibilities are 0 and 1. What the heck's happening here? One of the downsides of using linear regression for these binary outcomes is you can start to predict things that you can't interpret what the heck this means. Like, what does it mean if you predict 1.8? Does that mean, oh, it's 1? If you predict negative 0.9, what does that mean? It turns out that linear regression is not a particularly good fit to situations where you have these binary outcomes because there are certain assumptions that linear regression holds that are not the case for these binary outcome data. The two assumptions are constant variance, or what we call homoscedasticity, and an assumption of normality. In other words, when you're doing a linear regression, you're saying y is some linear combination of x with some coefficient plus some intercept plus some error, where that error is basically normally distributed with some constant variance. Let me show you what homoscedasticity, heteroscedasticity are intuitively. You can see them in the data sets I'm going to show you. Here, I'm going to show you a couple of data sets. The first data set is data that is clearly homoscedastic. This is data where there is a clear linear relationship and where the variance of that noise is constant. So let's take a look at what that looks like. Here, when we look at the data, we can see clearly a linear relationship. And if we look at the error, we can see that the error at any point is constant. It's 0 because there was no error added to this at all. So there's always a constant 0 error. The variance of that error at every point is the same. Now, I'm going to add a little bit of error into this, and I'm going to add some normally distributed error where we have a fixed scale parameter, a fixed standard deviation. So the error is the same at every point, and I'm going to graph it. And it turns out this is also homoscedastic. And when we look at it, we can see, yeah, there's a little bit of additional noise in the raw data. And we look at the error is all over the place. But notice that the width of that error is more or less constant at any point. The variance of that error doesn't change. Because, it makes sense. The error was introduced via a normal parameter, and that normal parameter had a fixed variance, a single constant variance. And so you can see that's kind of fixed. Now, you might not be sure what the contrast I'm trying to draw is. So what I'll do is I'll create another data set where the error is no longer fixed. Now, the normal has a scale that depends on the underlying data. So at some points, that error will be very large. At some points, that errors will be very small. And when we graph it, we begin to see a very distinctly different shape. Do you notice in the raw data how it's beginning to kind of fan out? And do you notice in the error that it's beginning to fan out? If we look at any vertical slice here of the homoscedastic, the variance from 0, the variance of that error is more or less constant, but in the heteroscedastic, that variance is growing. Well, it turns out that this is one of the core assumptions of linear regression, that the data is normally distributed, or at least the error is normally distributed, and that we have this constant variance term that it's homoscedastic. And this does not hold for binary outcomes. And this is in part why, at least mathematically, linear regression is not sufficient for binary outcomes. Instead, I want to introduce to you another approach, very closely related to linear regression, logistic regression. And the way I'm going to introduce it is, let's first look at what we might call the logistic function. And you may have seen things that look like this before. You may have heard this, people call a sigma or xbit in SciPy. Here, it's just a distribution, which has a scale and a location parameter. And it's just a distribution where the CDF is 1 divided by 1 of e raised to the power of, the scale is usually represented as the reciprocal, but the scale multiplied times the particular value. And it looks kind of like this. And you can think that what's going to happen with that scale parameter is it's going to change the steepness of the curve. So if I change the scale parameter, you'll see the steepness of that curve will change. You can see that's not very steep at all. And if I make this very small, you can see that's very steep. And you can think, if we're talking about binary outcomes, you can say, oh yeah, the zero's here and the one's here. Well, what I'm trying to do is I'm trying to take this logistic function and I'm trying to find the best values, not for the intercept and the slope like I would do in linear regression, but for that scale and location parameter of this logistic function. And in fact, we can formulate and hand calculate a logistic regression using just that approach. What we'll do is we'll say, this is our logit function, given some particular choice of scale. And I'll remove the location parameter because I'll just assume everything is centered. And then I'll make a little bit of the comparison a little bit easier, but we could always reintroduce it. It just makes the code a little bit more complex. Here's my logistic function, and here's my cost function. And I'll say, for my cost function, I'm going to take all the cases where I've guessed 1, all the cases where I've guessed 0, and I'm going to take just the logistic function at those cases where I guessed 1, and 1 minus logistic function at the cases where I guessed 0. If you think of that logistic function as a CDF, this basically means the probability of it being 1 in all the cases where I guessed 1, and the probability of it being 0 in all the cases where I guessed 0. And I'm going to do a negative log here just so this cost function can be minimized. And I have a bunch of candidates. Well, here is a really simple, really dumb brute force search through 100,000 possible values for what that scale parameter could be. And all I'm doing in a logistic regression is taking that logit and trying to find what the parameters of that are. In the linear regression, I'm just trying to find the slope and the intercept. In the logistic regression, I'm just trying to find the scale and the location. And that's it. That's all of the mechanism. I can do it with a very stupid brute force search, or I can do this with a slightly smarter scipy.optimize.minimize. I end up getting the same value. Or I could use stats models, and I can have stats models do a logistic regression, and I can ask it for the parameters. It is the same parameter. But notice, if I do this with scikit-learn, I do have to tell scikit-learn, please do not try and fit the intercept, because I've centered everything. And so this is why I chose to only vary the scale parameter, to not include the location parameter, because otherwise it makes comparing these a little bit harder. But you can see all 4 of these approaches give you the same thing. All logistic regression is a different function whose parameters you're trying to estimate by finding some cost function, and you're trying to minimize it. And you can minimize it either by using scipy.optimize.minimize and all of the solvers there. You can minimize it with a brute force search, or you can do whatever intelligence is lurking behind stats models or lurking behind scikit-learn. In the end, that's all you're doing with logistic regression. And the reason you're doing this is because these binary outcome data are not homoscedastic, and because, in truth, if you do a linear regression, you get some really weird predictive values. This will give you better predicted values. It'll actually give you 0 and 1 predicted values.